Hi, my name is Mac Mayer, and this is my Organic Chemistry Report 3. Here's my student ID. So first we will be looking at the difference between extraction versus washing. When looking at liquid-liquid separation, we are looking to remove our compound of interest from a solution. When performing our extraction step, the solvent that is used will be intended to retrieve our desired material. After some adequate mixing this in a separatory funnel, the mixture should form two immiscible layers. And immiscible means that the two layers, the two solutions within, do not mix with each other at all. Immiscibility can be the result of polarity, or also the solubilities of the solvents. A common pair of solvents used in extraction will be polar solvents and nonpolar organic solvents. The location of each solvent within a separatory funnel will be due to their densities. The solvent with the heavier density will be found on the bottom layer, and the solvent with the lighter density will be on the top layer. So here I'm going to demonstrate what an extraction would look like. First we have our mixture. Let's say our mixture has compounds that have different polarities in them. We're going to introduce a solvent that will be used to separate the polarities of our mixture. In a separatory funnel, we add our mixture and as well as the solvent. Then after shaking the separatory funnel, we will find that the solvent has separated our mixture into an organic compound layer and an aqueous layer. Both of these can be then drained out into separate beakers. We have now extracted the solvents that we were wanting, and they are now their own isolated compounds. After extraction, if you're looking to have a solid product, that is when recrystallization will be introduced to turn this liquid into solid form. Now we'll be looking at washing. Washing cleans our desired product from any impurities. Washing will be the process of selectively removing any unwanted materials or impurities within our mixture. This means that after washing, our solution should contain a layer of impurities that we do not want and then our product that we are wanting. For the washing to be successful, the solvent that we are adding to our solution mixture must be soluble with our unwanted compounds. This means that our product solvent that we are wanting and the unwanted solvent that we do not want must become immiscible with each other, which once again means that they do not mix and will form two distinct layers. So now I'm going to demonstrate what washing would look like. First we have our mixture. We have unwanted impurities within the mixture and we have our product that we are wanting to isolate. We also have a solvent that will have the unwanted impurities within the mixture to be soluble in it. We're going to add both of these into the separatory funnel. As we can see here, our solvent that we've added has mixed with our unwanted impurities, causing them to be immiscible with our product that we desire. Once we have our product, we can drain it into a beaker. This is what we will want to keep. With the unwanted solvent, we can drain it into another beaker and discard it, because this is just our unwanted impurities. We will now look at an unknown mixture that consists of 3 different compounds, and we will talk about the best way to separate each of these compounds into their purest forms. We have unknown 2. Unknown 2 consists of anthracene, piperidine, and oxalic acid. First, let's take a look at the solubilities of each compound. Anthracene is a solid neutral compound that is nonpolar, so it is insoluble in water, but it is soluble in alcohol, ether, and benzene. Piperidine is a basic liquid compound that is soluble in water and chloroform. Oxalic acid is a polar acidic compound that is soluble in water, but insoluble in chloroform. Looking at these 3 compounds, we know that if we mix each of them in water, our oxalic acid and our piperidine will dissolve, whereas our anthracene will not dissolve and will remain a solid. With this, we can decant this solution in order to isolate our solid anthracene, and we're going to place it in hot benzene. This will dissolve the compound as it is soluble in benzene. Then we are going to put it through gravity filtration in order to get rid of any impurities that we do not want within our solution. Once this is done, we're going to place our flask in an ice water bath in order to form precipitate. Once precipitation has occurred, we are going to move our solution through a suction filtration. This will isolate the solid, dry it out, and just separate it from our solvent that it was in. And finally, we are left with our final pure product of anthracene. Next, we will take a look at how to separate our oxalic acid from the piperidine. So first we have our oxalic acid and piperidine in a separatory funnel. We're going to add chloroform to this, as oxalic acid is insoluble in chloroform. The two layers will separate. From this, we can isolate our oxalic acid into a beaker, and we're going to put it in an ice water bath as well as with some NaOH pellets to help it precipitate. Once precipitation has occurred, we're going to put it through a suction filtration. Once again, this is just to isolate the solid and remove any of the solvent from it. And then we are left with our final pure product of oxalic acid. Now we still have our piperidine in this separatory funnel. We're going to add HCl to the separatory funnel along with the piperidine. The HCl will be used to wash the piperidine of any unwanted impurities. Once this is complete, we can drain our bottom layer of piperidine into a beaker, and that is our final liquid pure product. We are now going to describe the procedure of the organic synthesis lab. First, we had 3 NaOH pellets added into a distillation flask, along with 0.5 grams of 2-naphthalene, a stir bead, and as well as 5 milliliters of 95% ethanol. A condenser was put onto the distillation flask, and the mixture was refluxed for approximately 15 minutes. After all the solids had dissolved, using a pipette, 0.5 milliliters of iodobutane was added into the mixture. Near the end of the reaction, a sample of the mixture was taken in order to perform a TLC testing. The element used was ethyl acetate hexane. A spot was marked for the mixture, a co-spot, and also a competing spot in order to compare the product. The contents of the distillation flask were then poured over 10 grams of ice. The workup was to be done with ice in order to prevent losing any of our product. The final product was then collected and also used to perform a IR spectrum. We will now analyze the product of our organic synthesis lab using our TLC plate that was created and as well as our IR spectrum. When looking at our TLC plate, we see that we have an R spot, which represents the 2-naphthalene. We have a code spot that consists of the 2-naphthalene and the 2-butoxynaphthalene, as well as an S spot, which is just the butoxynaphthalene alone. The TLC plating technique allows us to observe the purity of our product. The TLC plate shows us that we have little to no impurities, as it is seen that there are 2 dots in the co-spot that match the RF values of the R spot and the S spot. Now we will take a look at our IR spectrum. When looking at our IR spectrum, it is seen that there are 3 peaks approximately at 3057, 2900, and 2800. These peaks here indicate CH bonds. Peaks shown at 1628 and 5099 over here will indicate our carbon-carbon double bonds. As there are 2 peaks shown, this will mean that there are 2 aromatic rings within this compound. It is not seen that there is any broad peak at around 3300. If there was, this would have represented an OH group from the 2-naphthalene. Therefore, there is no starting material within our product. We will now discuss what type of substitution mechanism this reaction underwent. For this organic synthesis, we were looking at an SN2 mechanism. A nucleophile attack along with a leaving group will be the key indication of an SN2 mechanism. We will first generate a moderately strong nucleophile by the deprotonation of the 2-naphthol using a sodium hydroxide in order to form methoxide. So here we're going to have this bond break and then have this lone pair take that hydrogen. And then this will be the product that we form. So now that we have our product methoxide, our nucleophile oxygen here will take its lone pair and it will attack the isobutane. Then we'll have our leaving group iodine break this bond and leave the isobutane. We are then finally left with our product of butoxylnaphthalene. We will now discuss some purification techniques that were used in our labs performed this year. First, we have crystallization or recrystallization. In this process, if we start off with a solid, we first have to choose a solvent that will dissolve this solid. This solvent will slightly dissolve our solid at room temperature, but will completely dissolve it when heated. Once the solution is heated, we immediately will pour it over into a gravity filtration in order to get rid of any unwanted impurities within our solution. After this, we will immediately take our solution and put it in an ice water bath in order to form our precipitate. Once precipitate has formed within our ice bath, we will take the solution and put it through a suction filtration. This will then extract any of the solvent from our solid, and it will isolate the solid product that we are wanting. Next, we have simple distillation. We use this process when we have a mixture of compounds that consist of different boiling points. What we want to do is we want to separate one of our compounds out of the mixture. This is done by putting the mixture in a distillation flask and attaching it with a condenser rod. Within the distillation flask, the mixture is brought to a boil. The more volatile or the compound with a lower boiling point will be the fastest to evaporate. The gas that has been evaporated from the liquid will rise up to the thermometer. Then it will proceed through the condenser rod. The condenser will cool the gas, causing it to condense and return back into its liquid phase, which will then come out the other end of the condenser and into our collecting vessel. Next, we will discuss differential extraction. This extraction is used to separate two immiscible liquids. The solution is poured into a separatory funnel, and it can as well be poured in with a solvent that will help the mixture to separate into two immiscible liquids, meaning it will form two distinct layers. So the solvents that are usually added will be solvents that match the solubility or the polarities of the compound we are wanting to extract within the mixture. Solvents that also relate to the acidity of our mixture can be added as well into the separatory funnel, such as HCl or NaOH if we wanted to react with an acid or base in order to separate our two compounds. That is another way to do it. Once the solvent is added into our mixture, the separatory funnel is shaken until our two layers have then formed. The bottom layer within the separatory funnel will be the compound that has the heavier density, and then the one on top will just have a lighter density. The layers can then be drained out of the separatory funnel into separate beakers, so that way they are now isolated. Next, we will discuss drying agents. A drying agent is an inorganic salt that readily takes up water in order to be hydrated. When placed in an organic compound, drying agents find extent application into purifying the chemical substance by the removal of water or any other impurities we do not want in it. Next, we will discuss chromatography. Within chromatography, there will be a stationary phase and a mobile phase. Compounds can travel from start to end at different rates. This all depends on whether they stick in the stationary phase or they float along the mobile phase. The chromatography techniques that were used for purification for these labs were the thin layer chromatography and also gas chromatography. The gas chromatography instrument has a metal column. Within the inside of the column, it is coated with the stationary phase. A sample that consists of more than one compound is injected into the column and pushed through by air, which will be the mobile phase. The organic compounds that flow out of the column are then seen on a peak chromatogram. The amount of time that it takes for a compound to travel through this column is known as the retention time. And then the peak height and the area that we are seeing on the chromatogram can then relate to how much of that compound was injected into the gas chromatography. Now we will look at our second chromatography, which is thin layer chromatography. The stationary phase will be the plate that is coated with the silica gel. We are then going to draw our start line on the TLC plate. A small spot of our solution of our compound will be put on one end. Next, we are also going to put a co-spot, which will consist of our solution and then another compound that we are wanting our sample spots to be competing with or to compare with. The plate is then going to be developed by placing it in a sealed jar that consists of an eluent such as ethyl acetate hexane. This eluent will be considered the mobile phase, as once placed in the jar, it'll move up the TLC plate up to a certain front. What the eluent will do will then carry these spots up the plate as it moves up the plate. If more than one component was present in our sample, then it will consist of two spots. If we also notice that there are RF values that match the spots within the other lanes of the plate, then this will indicate that these compounds are also within our sample compound. We will also find that the more polar compounds will be closer to the bottom of the plate, whereas the less polar compounds will be more at the top of the plate. With this technique, we are now able to identify the purity of our compound. Another technique that was used was formulating an IR spectrum. IR spectroscopy can be used to identify any functional groups within our compound. These functional groups each have their very own characteristic absorptions, which will then be shown within the IR spectrum. We read these functional groups by looking at the location of their peaks within the IR spectrum. When looking at these functional groups, we can then easily indicate what our compound consists of and what its chemical structure may look like. Another thing we can do is use it to look at the purity of our compound. If there are any functional groups that are seen within the IR spectrum that we know are not within our compound, then that can indicate some impurities. Whereas if we see all functional groups that are consistent within our compound, that means our compound is then pure. The last technique used was determining the melting point of a substance. Melting points can be experimentally measured using a melting point apparatus. The melting point will be pure if its experimental melting point matches that of the theoretical melting point. The presence of any impurities within a substance will lower its melting point and will differ from its theoretical melting point. If the melting point of the substance is correct, then therefore it is known to be pure. That is now all for this Organic Chemistry Report 3 video. Thank you for watching.